One of the challenges with measuring strain in particular is that my measurements can be influenced by factors beyond strain. So temperature is a pretty big one. Temperature can change the resistivity of whatever my strain gauge is made out of. So whatever metal that is or alloy that is, temperature can change the resistivity, and that will ultimately influence my strain measurement. To write that down more formally, let's go back to our original definition where we had our delta R over R was equivalent to our gauge factor times the strain. So this is a change in resistance in my strain gauge over the nominal resistance of that strain gauge. Is going to be gauge factor times strain. And so if I think about this in terms of temperature, I can think about this as equivalent to a thermal coefficient of resistance, TCR, times a delta T. So TCR is my thermal coefficient of resistance. That's often given in something like parts per million per degree C per degree F sometimes. And my delta T, of course, is my temperature change over the course of the measurement. And then it can be across the bridge as well, as we'll talk about a little bit later. All right, but using this, and I can give you a couple example TCRs. So the TCR, the thermal coefficient of resistance of Constantan, which is probably one of the more common materials that, or alloys that strain gauges are made out of, is only 6 parts per million per degree F. The thermal coefficient of resistance of an isoelastic alloy is going to be something more like 260 parts per million per degree F. And if I use something like nickel, it's more like 1,000 or more parts per million per degree F. So you can see how these can get pretty big over time. But one of the reasons Constantan is so popular is because it has this low thermal coefficient of resistance. All right, and looking at this part of the equation here, I can calculate a equivalent strain, right? It's not a physical strain, it's not a real strain, but an equivalent strain that my change in temperature and my thermal coefficient of resistance is actually getting me. So I'm going to call this epsilon EQ with a comma T for temperature. And so this is going to be that thermal coefficient of resistance times my change in temperature divided by my gauge factor. And gauge factor for something like Constantan is 2. For this isoelastic alloy is something like 3.5. So let's plug that in and actually see what we might get for the isoelastic alloy. And let's do that for a single degree, so we get some sense as to how much this is moving. 5 by 3.5. And this is going to be equal to a whopping 74 microstrain. Which microstrain, so it sounds small, but this can actually be quite large if I'm trying to measure a system that has very small strains. If I only have a 1 degree F temperature change, right, and that can change quite a bit just throughout the course of the day, right, I'll get a pretty wildly different strain measurement here. So ultimately, the strain that I'm measuring from my strain gauge is giving me my actual strain. Let's call it an axial strain just to give it a name, plus a temperature strain, right? A strain due to that temperature change, or I can call that what I called it up there, EQT. Okay, and the magnitude of this is going to depend on the material that my strain gauge is made out of and the kind of temperature variation I might be seeing in my environment. Let's assume that we're stuck with that. We have some material, maybe we have that isoelastic material for our strain gauge, so I have this very high sensitivity to temperature. How can I actually compensate for that? So here I have a beam of material, and I'm going to laminate my strain gauge on top of that. And so now we're saying that this is going to be measuring my axial strain that I get from applying this axial force to the end of the beam, plus some strain due to temperature changes in this environment. And if I just left it with this, I would get some pretty noisy results if I have some reasonable temperature fluctuations. But one thing that I can do is have a separate slab of material that is not actually, has no force being applied to it, I can have a second strain gauge on this material that's being co-located with this, so it's influenced by the same temperature changes. So in this case, it only sees that equivalent strain due to temperature change and not any axial strain. And I can set those two strain sensors up in a bridge circuit where I have effectively my active strain gauge in this quadrant of the bridge circuit, and down here I have my compensating strain gauge and then static resistors on this other side here. So this is a half bridge, right? I have two strain sensors here. So if I look at the output of this bridge, I can look at this as a full bridge and then just set R3 and R4 to 0. So I have my gauge factor over 4 times epsilon 1 minus epsilon 2 minus epsilon 3 plus epsilon 4. Right? These two are 0, as I just mentioned. And so now I'm left with strain 1, which is my epsilon A plus epsilon T, so we'll write that in there, and then minus my epsilon 2, which is just measuring that equivalent strain due to a temperature change. So you can see now how these are going to cancel, and I'll just be left with my axial strain. So in this case, I've used an extra strain gauge that is actually not measuring any axial strain, and I've co-located that, meaning I place it close to my strain gauge that's actually undergoing the strain that I want to measure. And using that, I'm able to compensate for any temperature changes that both of those see. Now the co-location is important because if I have one of my strain gauges in one place, another strain gauge way over here, and I have temperature variations between those two locations, right, this no longer works. So I need these things located very close to each other. And I can compensate for things other than just temperature. So say I have a beam of material and I only want to measure the axial strain, but this thing is being bent as well. So I want to reject that bending strain and only measure the axial strain in this cantilever beam or this general beam of material. So if I write that down, I'm trying to measure my axial strain and reject my bending strain that I might get from trying to bend that beam. And so I can think about how I'm going to get terms to cancel. And one way to look at this, in this case, is if I have a strain sensor on both the top and the bottom of my beam, right? This one is going to see some EA, or epsilon A, plus my bending strain. And this one down here is going to see that same axial strain, but minus the bending strain because that bottom edge of the beam is in compression. Right? And so once I've realized this, I can figure out where to place these in my bridge circuit so that those epsilon B's are going to cancel out. Right? I need those to be terms that add. So if I write down that full bridge equation, I'm going to need these to be in the terms that add. So I'm going to need one of these in epsilon 1. So let's say that's the epsilon A plus epsilon B term. I'm going to need the other to be in epsilon 4, epsilon A minus epsilon B. In this case, I only have two strain gauges, so I can just cancel the two other ones. So if I plug these in, I'm going to get a gauge factor of 4, or GF over 4, my gauge factor over 4, times epsilon A plus epsilon B, which is my bending strain, plus epsilon A minus epsilon B. And so now those bending strains cancel, they're rejected like I wanted them to be rejected, and I also get an additional amplification or additional factor of 2 in my output for that axial strain. So my VO over VI is equal to the gauge factor over 2 times that axial strain. And so once I figured out that I want to place them here, I can sketch my bridge circuit. So I've left the 4 spaces open for either resistors or strain gauges. Remember, this is 1, 2, 3, and 4. So I decided 2 and 3 were both going to be resistors, right? Because those were some other terms that I didn't need. So then my strain gauges are going to go into epsilon 1 and epsilon 4. And specifically, this top one is strain gauge 1. So that matches up over here. And this bottom one is in the 4th position over here. So based on the compensation that I wanted to do, I wrote out my full bridge equation here. And I figured out where I wanted to plug in my different strains so that I got the term to cancel that I wanted to cancel. And then I used that to sketch out my bridge circuit and figure out where I'm going to place those strain gauges in the bridge circuit to actually do that compensation. So now I can actually measure only axial strain even though this beam might be bending and stretching.